Today we are going to discuss about fundamental theorem of homomorphism of groups. The fundamental theorem on homomorphism, also known as the fundamental homomorphism theorem, relates the structure of two objects between which a homomorphism is given and of the kernel and image of the homomorphism. The homomorphism theorem is used to prove the isomorphism theorems. So recall some basic definitions. So group, subgroup, normal group, quotient group, homomorphism, epimorphism, isomorphism, and kernel of F. So what is a homomorphism? In algebra, a homomorphism is a structure preserving map between two algebraic structures of same type, such as two groups. So now we define the homomorphism. A map from a group G into a group G dash is called homomorphism if f of a b equal to f of a into f of b, or f of a plus b equal to f of a plus f of b. For example, f from z comma plus tends to z comma plus defined by f of x is equal to 2x is homomorphism. Since f of x plus y equal to 2 into x plus y, so we can expand that term equal to 2x plus 2y according to the definition of f of x. So 2x means f of x, 2y means f of y. So now we can get it f of x plus y equal to f of x plus f of y. Therefore, f is homomorphism. So taking the another one example by using multiplication, f from r star comma dot tends to r plus comma dot defined by f of x is equal to mod x is homomorphism. Since f of xy equal to mod of xy by definition of x, then mod of xy is going to expand mod of x into mod of y. Then according to the definition, mod of x means f of x, mod of y means f of y. So now we can get it f of xy equal to f of x into f of y. Therefore, f is homomorphism. So now we want to go through another one example which is not homomorphism. F from r plus comma dot tends to r plus comma dot defined by f of x is equal to 2x is not homomorphism, since f of xy according to the definition which is equal to 2 into xy, but f of x into f of y equal to 2x into 2y. So we can get it that value equal to 4 into xy. So by using f of xy and f of x into f of y, we can say that the both values are not equal. Therefore, f is not homomorphism. So now we can define some other definitions. Let f from G tends to G dash be a homomorphism. If f is onto, then f is called an epimorphism. If f is 1, 1, then f is called monomorphism. For example, f from z comma plus tends to z comma plus defined by f of x is equal to 2x is homomorphism. By looking at the picture, first picture, the domain set is z and the codomain set is also z. But the codomain set is divided into two categories. One part is odd values, another part is even value. So by the definition, we want to take it every element in the domain set have an image in the codomain set as a even numbers. So every element in the codomain set domain set have a image in the codomain set, so which is satisfied 1, 1 condition, but which is not satisfied on 2, since every odd element in the codomain set does not have a pre-image in the domain set. So therefore, the given example satisfied 1, 1 condition and homomorphism condition, so that which is monomorphism. Now we take it another one example. F from R star comma dot tends to R plus comma dot defined by f of x is equal to mod x is homomorphism. By look at the picture, the domain set is R star, the codomain set is R plus. So every element in the domain set have an image in codomain set. At the same time, every element in the codomain set have a pre-image in the domain set. So which is satisfied onto, but which is not satisfied 1 1, because in R star both positive value and negative value get the same image in R plus. For example, 1 and minus 1 have the images 1. So therefore, which is not satisfied 1 1. So the given example satisfied onto and homomorphism. Therefore, the given example, that is a given function, is known as the epimorphism. So now we define isomorphism. Let f from G tends to G dash be a homomorphism, and if f is 1 1 and onto, then f is called isomorphism. For example, f from Z comma plus tends to 2Z comma plus defined by f of x is equal to 2x is isomorphism. If you look at the picture, domain set as Z and codomain set as 2Z. Okay, so every element in the domain set have a separate image in the codomain set. Also, every element in the codomain set have a pre-image in the domain set. So which is satisfied 1 1 and onto, and also which is satisfied homomorphism. For say, here we take it for f of x plus y is equal to 2 into x plus y. So then we can write which is equal to 2x plus 2y equal to f of x plus f of y. That is f of x plus y equal to f of x plus f of y. So which is satisfied 1 1 onto as well as homomorphism. Therefore, f is isomorphism. So now we take it some examples for which is not isomorphism. Let f from R star comma dot tends to R comma plus. Here f is not isomorphism, since in R star comma dot we have more than one element have a finite order. Say example 1 comma minus 1. The order of 1 is 1, the order of minus 1 is 2. In R comma plus, only one element have a finite order, say 0. So the given function is not isomorphism. And also we earlier discussed the two examples, the first one and second one. So clearly we know that first one is monomorphism, which is not satisfied onto condition. The second one is epimorphism, which is not satisfied 1 1 condition. Therefore, the two examples are not isomorphism. So now we define the kernel of f. Let f from G tends to G dash be a homomorphism. Let k is equal to set of all x such that x belongs to G, comma f of x is equal to E dash. So suppose if we consider any element belongs to k, then that element belongs to G also, as well as f of x is equal to, we get the image identity element in G dash. That is the image of that element is known as the identity element in G dash. Then only we can consider that element in K. So therefore, then K is called the kernel of F and is denoted by kernel F. For example, F from Z comma plus tends to 2Z comma plus defined by f of x is equal to 2x. So here what is kernel of f is equal to 0. Suppose if we taking any element from Z Then according to the definition f of x is equal to 2x, we put f of 0 that is equal to 0. So 0 also belongs to 2z, which is the identity element in 2z under addition. So that 0 belongs to kernel of f. So now we are taking for another one example, f from r star comma dot tends to r plus comma dot defined by f of x is equal to mod x is homomorphism. So what is kernel of f here? That is 1 comma minus 1, because every element in R star, that is we can consider for positive value as well as the negative value. Okay, so that both value have an image as a positive value only in the codomain set. So therefore 1 comma minus 1 have an image as 1, which is the identity element of R plus. So that the kernel of f contain 1 comma minus 1. So now we are going to discuss about fundamental theorem of homomorphism. So what is the statement? Let f from G tends to G dash be an epimorphism. Let K be the kernel of f. Then the quotient group of G modulo K is isomorphic to G dash. So what is the proof? First we are going to define the function pi from the quotient group G modulo K tends to G dash by pi of Ka equal to f of a. We want to show that pi is isomorphic. Okay, so it is enough to prove pi is the following condition. First, we want to check it the given or the defined function pi is well defined. Then we want to verify which is satisfied 1 1 and onto and homomorphism as well as isomorphism. If all these conditions are satisfied, then we can say pi is isomorphic. So now first we are going to show that pi is well defined. If we want to show that pi is well defined, we want to prove that Ka equal to Kb. This implies pi of Ka equal to pi of Kb. So let Ka equal to Kb. So according to the right cosets, Ka equal to Kb means any one of the element belongs to the another set. So A belongs to Kb. So now we assign some particular value to the A. So by A is equal to Kb, where K belongs to the set K. Now we take function f of A equal to f of Kb. Since f is homomorphism, so we can write f of Kb equal to f of K into f of B, since f is homomorphism. According to the definition of kernel, f of K equal to the identity element. So f of K equal to E dash. So we can write f of A equal to E dash f of B. So if you multiple with any element with identity, we get the same element. So that E dash f of B means we can get it f of B. So f of A equal to f of B. According to the definition of pi, f of A means pi of Ka, f of B means pi of Kb. So we can get it Ka equal to Kb. This implies pi of Ka equal to pi of Kb. So from this we conclude that pi is well defined. So we verified that pi is a well defined function. So now we go to verify other conditions so that pi is 1 1. If you want to show that pi is 1 1, we want to check pi of Ka equal to pi of Kb. This implies Ka equal to Kb. So let pi of Ka equal to pi of Kb. That is according to the definition of pi, we can get pi of Ka means f of A, pi of Kb means f of A. So this implies f of A equal to f of B. Then we bring f of B into the left hand side. So f of A into f of b whole inverse equal to e dash. That is identity element. Okay. Then f of a into f of b inverse equal to e dash. Since f is homomorphism, then f of b inverse equal to f of b whole inverse. So that instead of f of b whole inverse, we can write f of b inverse. Okay, both are same only. F of b inverse equal to f of b whole inverse. So now f is homomorphism, so we can write f of a into f of b inverse equal to f of ab inverse. Okay, so f of ab inverse equal to e dash from the previous one. F of ab inverse we can write equal to e dash. So according to the kernel definition, f of ab inverse equal to e dash means that ab inverse belongs to k, since by the definition of kernel of f. So we can write f of ab inverse equal to e dash. That means ab inverse belongs to k. So then using the right coset definition, AB inverse belongs to K means A belongs to KB. Again using the right coset definition, A belongs to KB means KA equal to KB. So now we verified that pi of KA equal to pi of KB. This implies KA equal to KB. Therefore pi is 1 1. So now we want to go to check pi is onto. So let A dash belongs to G dash. Since f is onto, there exists A belongs to G such that f of A equal to A dash. Hence pi of Ka equal to f of A equal to A dash. That means every element in the codomain set, say A dash belongs to G dash, have a pre-image in the quotient group of G modulo K. That is a Ka. Okay, so every element in G dash have a pre-image in the quotient group of G modulo K. Therefore pi is onto. So now we show that pi is homomorphism. If you want to show that pi is homomorphism, we want to verify pi of Ka into Kb equal to pi of Ka into pi of Kb. So we want to show that is a pi of Ka into Kb equal to pi of Ka into pi of Kb. Now we take in for pi of Ka into Kb and to show that pi of Ka into pi of Kb. So according to the right coset definition, pi of Ka into Kb means pi of Kab. Okay, according to the definition of pi, we can write pi of Kab equal to f of ab. Then f is homomorphism, so we can write f of ab equal to f of a into f of b. Then by the definition of pi, we can write f of a equal to pi of Ka, f of b equal to pi of Kb. Therefore we can get it f of a into f of b means pi of Ka into pi of Kb. So now we proved pi of Ka into Kb equal to pi of Ka into pi of Kb. So we proved that pi is homomorphism, since pi of Ka into Kb equal to pi of Ka into pi of Kb. So now we verified all these conditions. That is pi is well defined, pi is 1 1, pi is onto. Okay, pi is homomorphism. Therefore we can say that pi is isomorphism from the quotient group of G modulo K onto G dash. Therefore the quotient group of G modulo K is isomorphic to G dash. So now we see one example to verify the fundamental theorem of homomorphism. Take the example, the quotient group of R star modulo the group 1 comma minus 1 is isomorphic to R plus. So look at the diagram. R star contain the both positive value and real value, that is a positive real number and negative real number except 0. In the domain set we can consider only the positive real numbers. Okay, so now according to the definition, f from r star tends to r plus defined by f of x is equal to mod x. So if you look at the picture clearly, every element in the domain set have a image in R plus, but which is not 1 1. But at the same time, every element in the codomain set have a pre-image, so which is on 2. So according to the fundamental theorem of homomorphism of group, F is epimorphism and K the kernel value. The kernel value F is here 1 comma minus 1. Since that 1 and minus 1 have an image in the codomain set as 1. So therefore the kernel of F is equal to 1 comma minus 1. If it exists, then we can say that R, that is a quotient group of R star modulo the group 1 comma minus 1 is isomorphic to R plus. Okay, so according to the fundamental theorem of homomorphism, here the function f is epimorphism and kernel f is equal to 1 comma minus 1, so that we can easily say that the both groups are isomorphic. So here we can take it another one picture. In the domain set, we can consider every element as like order a comma minus a or minus a comma a. Okay, b comma minus b, like that we can consider for every element in the domain set. Okay, then each element in the domain set have a image in the codomain set as a positive value only. For example, a comma minus a or minus a comma a means it is have a image in R plus as a, so that here we can combine every element in that domain set have a separate image in the codomain set. At the same time, every element in the codomain set have a pre-image in the domain set, so which is satisfied 1 1 and on 2, and also which is a homomorphism. So therefore that given example is isomorphic for the given two sets. So thank you for watching my video. Thank you once again. Thanks a lot.